Okay, great. Yes, so respond to the online poll, and yeah, we'll get started. It's week 6 Friday, so we're just like a month away from being done with school. It's kind of crazy. All right, so we got a midterm next week on Wednesday. And I decided to list off, I think, possible problems and topics that I'll throw on there. I'm still writing it, and so I'm going to show you a bunch of stuff. And I'm basically deciding between some problems that I've got in mind. Okay, so I think all of this is pretty standard. So it's Wednesday, regular time right here, 45 minutes, handwritten. I'll send out a seating chart, okay? I'm most likely going to have 4 problems, okay? And I'll tell you kind of what I'm planning. I'm just, as I write these, part of the thing when you write a test is you want to try to make sure your problems are unambiguous. Like, you don't want to be like, I don't want to have to go around like answering everybody's questions about the problem. So you're trying to write it unambiguous and clear, and you also want to make sure it can be completed within 45 minutes. So I think I'm going to like show you like 6, like an assortment of 6 things, and I'll pick 3 out of the 6. Okay, so here's one possible thing. So one is, we'll have neural networks, and then I will ask you to do a numeric gradient calculation, okay? And so I'm gonna have like a very simple neural network, and because you gotta do stuff by hand, it's probably going to be something like 2, 2, 1, like 2 nodes in the input layer, 2 nodes in the hidden layer, 1 node in the output layer, right? And then, so you'll have like 6 weight parameters, 2 by 2 on the first weight matrix, 2 by 1 on the second weight matrix. Maybe some bias vectors, not entirely sure. And as far as the activation functions go, I would keep it simple. Either identity or a ReLU, which we haven't talked about, but the ReLU is basically identity if x is positive, and it's 0 if x is negative. And as far as numeric calculations go, it's very simple. Identity, you don't have to do anything to it, right? And then if it's ReLU, if it's negative, you make it 0. And I won't, like if it's numeric gradient calculation, I won't use the sigmoid, because the sigmoid is a little bit of a pain to like have to type all of that into your calculator and do like, e to this and that. Loss function will be squared loss, and I'll provide, probably a small set of input data, maybe like 2 observations, just because if we're doing squared error, you have to do it for each observation, and if you get really over 3 observations, it becomes, again, a pain to compute. And then, I'll give you some weight matrices, and you'll find the gradients numerically for one of these things, which means you like, you add, perturbation like 0.01 or something, see how it affects the result, and that's that. Okay, so that's numeric gradient, and I think the point of this is to just kind of make sure that you understand, I guess how things propagate forward, but also understand how that can be used to calculate your gradient, at least from a numeric standpoint. Okay, so that's one option. I'm debating between this problem and this problem, which is going to be an analytic gradient calculation. So this is more like a back propagation thing. Again, you'll have a simple neural network setup, probably a 2, 2, 1. I'll specify some kind of activation function. And for this one, I will not use the ReLU, because the ReLU is case-wise, whether it's x positive or not, which forms a discontinuity in the gradient or the derivative and that complicates things. So it'll be either the identity or the sigmoid, okay? And gradient of identity is 1, and derivative of the identity is 1, derivative of the sigmoid, I think is something you can calculate or figure out yourself. And I'll at least provide this definition of the sigmoid in case you forget. You'll have to figure out the sigmoid prime yourself. Loss function, squared error loss, small input data, provide some initial weight matrices, and then you'll find the gradient with respect to one of the weight matrices or bias vectors, okay? And then, I'm kind of debating between these two neural network type problems. I think, if I include both of them, I think it's too much work. So one or the other, be ready for either one. Is that okay? And then I'm debating between another two regarding MLE/Fisher information, and again, writing these out, trying to decide. Okay, so this one, I'll give you some kind of MLE model, which will be a probability distribution with one parameter. So I think in class we looked at things like the Bernoulli. Okay, there's other distributions with single parameters, things like I don't know if I want to list them off, but you should be familiar with some distributions, right? And I'll provide, I'll give you the PDF of the distribution, okay? And then I'll provide some kind of sequence of data that was observed from the distribution. And based on that sequence of data, you'll find the maximum likelihood estimate of the parameters based on the observed data, okay? So you'll figure out your likelihood, which is the product of each of those individual probabilities. And then you'll probably take the log likelihood and maximize that using derivatives and setting that to 0. And then I'll ask you to calculate the Fisher information, okay? And I'll provide the definition of the Fisher information, which in our case we're going to just use the negative expected value of the second derivative of the log likelihood with respect to the parameter, okay? So I'll at least provide this kind of equation, which should be enough to kind of jog your memory regarding how to go about finding Fisher information, right? But we had a discussion, or at least in one of the lectures, that the second derivative measures kind of curvature, how quickly the slope is changing, so the curvature, and if we take kind of the expected value of that, it gives us a sense of how much information we have about our parameter. So that's one possibility. And then the other thing that I'm considering, okay, regarding kind of this MLE/Fisher information topic, would be having you find the Fisher information matrix of a distribution with 2 parameters, okay? So if I do this one, it's going to be a distribution with 1 parameter. This one will be a distribution with 2 parameters, something like the normal distribution, or I'm debating a few things. Some of the distributions get real complicated real fast as soon as you start trying to calculate derivatives with respect to the parameters, and so I don't want to put that burden and curse upon you. I think the normal distribution is fair, and so anyway, I would provide the PDF of this distribution, and I'll give you the expected value of the distribution, and then you'll find the Fisher information matrix, right? And so in our case, because we've got 2 parameters, your Fisher information matrix will be 2 by 2, okay? So if you've got parameter A and parameter B, your top left will be kind of the second partial derivative with respect to A and respect to A, and then your lower right will be the second partial derivative with respect to B and respect to B, and then kind of the ones on the off diagonal would be there's partial derivative with respect to A, then respect to B, and then respect to B, and then respect to A, second partials of this. Okay, now, and I'll at least provide this equation here, so just to kind of, again, jog your memory, but you need to be comfortable with this, right? So we can kind of find the Fisher information matrix by taking the negative expectation of the Hessian of the log of the PDF. So it's a lot of log PDF derivative stuff, okay? So again, topic 3 or topic 4, these are some possibilities here. Okay. Is that okay? All right, and then the last one will be a Bayes classifier, and these are basically the same problem. I'm just debating what PDF to use. And so one will be like a binomial Bernoulli thing, okay? And this is going to be, if it's that, then it's really similar to the example that we had with the red and blue marbles and the different bags and things like that. And so I'll kind of, the data comes from some kind of mixture of possible classes, and each class has a different proportion of success. And I'll provide basically the summary of the training data, which includes the counts of the classes and the MLE estimates. And then I'll provide basically a new test case, and based on that new test case, you'll figure out the Bayes probability of each class. Okay, so using a Bayes classifier there. Or if it's not the binomial example, then I will have a mixture of Gaussians, okay? And so it'll be like, one class has, mean this with this standard deviation, another class has mean this and this standard deviation, maybe something else has another class of mean this and this standard deviation. And then I'll give you a measurement, and I'll say based on this measurement, and also kind of the, your prior counts of classes, which we'll use, you'll use as your prior distribution or prior probabilities. You'll figure out your Bayes probability. Okay, so this is the Bayes classifier for basically a fairly simple thing. It's not going to be no multivariate Gaussian for this thing. Okay, that the only so you got a Bayes classifier problem there. Okay. Questions? And then the last, just some short answer conceptual questions. I'm not going to tell you what they are, but like a possible example would be something like, what's the naive assumption of the naive Bayes classifier, and what advantage does this assumption provide? And you would tell me, covariance between predictor variables is 0. Yes, that's the naive assumption. Okay, and the advantage of that is, well, fewer parameters to estimate. You don't have to estimate covariance because you're just going to assume it's 0. And also because you're not estimating those things, you don't have to worry about your estimates being skewed by the data as well. Okay, stuff like that. All right, so just kind of conceptual questions, and kind of the topics that will be covered here will be the neural networks, MLE, Fisher, Bayes and naive Bayes classifier. Okay, so pretty much through, I don't know, I guess Wednesday's lecture. Okay, and then today we'll cover a new topic. It's actually really super simple and not that complicated, but it's an important method, and so we'll cover that today. Okay, but any questions about the midterm? Okay, so that's Wednesday, and again, I'm still writing it up and trying to figure this out. I think this gives you a good list of topics to study, though. Okay, I'm also working on writing up your next homework assignment, which will be on kind of these classification methods that we're covering. So we've covered the Bayes classifier. Today we'll look at k-nearest neighbors, and next week we'll look at support vector machines, and I have to write a homework that deals with that. So anyway, that's what we'll do. No, the exam's on Wednesday, right? So I might like release a homework, but it's not going to be due before the exam. That'll give you like 3 days to work on it. I don't know. I guess no, I wouldn't do that. I think this list is comprehensive enough that if you study all the topics here, you'll be prepared for the exam. Okay. All right. So, well, we'll see. You know, K nearest neighbors. I don't know how complicated this is and how in depth we need to get. Okay. All right. Classification. K nearest neighbors. This is how the algorithm is set up. It's really just this one page here. Okay. You got training data. All right. And all of the training data is labeled with a class, right? So if you got 1,000 observations in your training data, you're going to have 1,000 classes. Every single observation in your training data is labeled with a class. Your training data can be, you know, however many dimensional as it needs to be. Okay, 1-dimensional up to super high dimensional things. You can use KNN for like image classification. It does a terrible job, but you can. It's not wrong to do it. Yes, question.
What do you mean by class?
Like, yeah, it's so because this is a classification algorithm, right? So maybe there's 2 classes, class A and class B, all right? And every observation is going to be labeled with either that it belongs to class A or belongs to class B, okay? If you wanted to do KNN for image classification and it's going to perform poorly, you can have like 10 different classes of images. You can have like, this is pictures of cat, and this is picture of dog, and this is picture of car, or something like that. Every image is labeled with a class, and then however many pixels your image is the dimensionality of your data. So if your image is 50 by 50 pixels, then your data is 2500, dimension of 2500, okay? And so you'll have a new test case, right? So the KNN, what it does is it takes in a new test case, and the first thing you're going to do is you're going to measure the distance, and this is generally the Euclidean distance, but there's no rule against using the Manhattan distance, the kind of the L1 distance, or some other metric of distance, okay? But most frequently we're using square root of the sum of squares. So that's the Euclidean distance from the test case to every single other point in the training data, okay? So depending on how big your training data is, this first step can become very computationally expensive, right? Because we'll have a visual representation and your eyes can easily see like, oh, we really only need to check like a few of these points. That's true. But as far as it being in a matrix, there's no like quick and easy way to know which points are the closest without going through the step of actually measuring the distance to every single other point, okay? So you've got to measure the distance to every single other point. Then second step is you sort them from least to greatest, and then you're going to select basically the K observations with the smallest distances, okay? So if your K, maybe I should have said K is some integer, okay? So if K is equal to 1, you're going to pick just the closest observation, and if K is 20, you'll pick the top 20 closest observations, okay? And K can be, any integer you want, yeah.
Since you're using Euclidean distance, does it mean that your predictor variables have to be
Do my predictor variables have to be what? Numeric? Yes. I'm sorry. Maybe I need to write that here, okay? Yeah, predictor variables need to be numeric. I mean, I suppose you could turn a categorical variable into a 0-1 type of deal, but generally, yeah, your predictor variables are numeric and they're on the same scale, okay? And so you pick the k observations with the smallest distances, and then the class with the highest representation among those k nearest neighbors is selected as the class of the test case. All right? And then how do you decide which k to use? Generally, we just say use cross-validation and see how your prediction performance is on a validation set. So k nearest neighbors, it's very simple. It's not favored in practice because of this. During the classification step, this step, first, number one, measuring the distance to every single other point in the training data is generally an expensive step, okay? Resolving ties, this is an issue that comes up. If there's only two classes and you keep k odd, you won't get any ties. So that's just kind of your general rule of thumb. Keep k odd, and you won't have as many ties. But if you have k is even, or if you have more than two classes, so you can have like k equal 5, but if you got 3 classes, when you pick your 5 nearest neighbors, you might get 2 of class A, 2 of class B, and 1 of class C, okay? And now how do you decide between class A and class B? Then we have some suggestions for how to deal with ties, but there's no consensus that says this is the best way, okay? These are all different compromises of ways to deal with ties. So one is you just say, I can't classify this because there's a tie in this, there's a tie, okay? So we're gonna leave it unclassified, okay? Another option is to switch to the one nearest neighbor. Generally, you won't have a tie when you have the one nearest neighbor. Usually, it will only, it's like only if you pick exactly on like the halfway point between two classes will you get that. But generally very low probability, and so switching to the one nearest neighbor will generally result in no ties. Or you can select randomly among the top tied groups. So if you have 2 of A, if you have K is 5 and you got 2A, 2B, and 1C, you can just randomly select between A and B. Those are the ones that are I forget what I said. Tied groups, okay? Or lastly, you can say among the tied groups, select the group with the closest neighbor, okay? So, which is not necessarily the same as switching to the one nearest neighbor. So if you have a situation where you've got 2A, 2B, and 1C, it could be that the one nearest neighbor is C, and so you can decide to pick that it belongs to class C. Or you can just say, well, with K equals 5, we've got 2A and 2B, and so between A and B, A has an observation that's closer, and so we're going to pick A, all right? So these are just different ways, and resolving ties can be an issue when you have more than 2 classes, and so that can happen, and these are just different ways to deal with it. Okay, is that all right? Okay, so I just have some pictures here. We might finish early today. So I'm going to just take some random data from 2 multivariate Gaussians. Okay, so I'm going to generate 14 points from one multivariate Gaussian where the mean is -1, 0, centered here, and it's going to have no covariance. Okay, basically the identity matrix is my my variance thing, okay? And then I've got XB, where it's centered here, 10 observations. It also has an identity matrix, or diagonal matrix, but slightly more variance here, okay? And I'll kind of bind these together to create my training data X. I figure out my kind of just the plotting margins using the min and max. Oh, this has a typo. This should be a 1 here. I'll fix that. This should be a 1. Okay, so the left and right will be the min and max of column 1, and the bottom and top will be the min and max of column 2 as far as plotting goes. And then so I'll just plot all of these things, using the margins left and right. When you're plotting k-nearest neighbor stuff, I don't know if it's super important, but I think it's like visually, I think it's important to use aspect ratio equal to 1. Okay, because when we're talking about the closest distance, you're basically drawing like a circle around your point, and if you don't have aspect ratio equal to 1, that circle can look like an ellipse, and it can be confusing to say, oh, this distance which is long in the x direction is equal to this distance which is, our brains just doesn't like stuff like that. So anyway, aspect ratio equal to 1. So anyway, if I plot this, this is kind of just what our training data looks like. And I think for my first test case, I pick 0, -1. So I'm going to put a test point right here, okay? And then we're going to use k-nearest neighbors to figure out which, how we should classify our test case here, right? And so, I don't know. What's your opinion? Red? Blue? Okay, and the answer is it depends. So, as always. Okay, so the idea is we're gonna take this and we're gonna measure the distance to every single other point. Okay, so you have to take this, measure the distance to every single other point. Okay, and then you're gonna pick the k shortest distances. Okay, I don't show the code behind all of this because it's going to be a homework assignment. Right? But you get the pictures, okay, and I guess my explanation, which I don't know how great it is. Okay, but here's our test case. We measure the distance to every single other point, and so if you choose k equals 1, okay, this is the closest point, and I've drawn a circle with this, using this as its radius, and we can see, indeed, this is the closest point. And so this is going to classify it as red. Okay. If I do k is 3, okay, this is the third closest point, and we'll get it's going to get classified as red, okay, because we have 2 red versus 1 blue. So you pick the class with the highest representation among your k nearest neighbors. Okay, so among the 3 nearest neighbors, we've got 2 red, so we're going to choose red. Okay. At k equals 5, it would get classified as blue. Okay, so at 5, the 5 nearest neighbors are these ones in this circle here. Okay, and we can see there's 3 blue and 2 red. Okay, and if we go to 7, okay, this one is not the nearest. Okay. Oh wait, I made a mistake. 7 will choose blue, okay? Okay, I gotta fix this, okay? Yeah, it says 7 chooses, but it says 4 blue and 3 red. Okay, I fixed this part, but not this part. Okay, so I've made a mistake there. But yeah, at 7, it's gonna be blue, okay? So this point will be blue if k is 7, and because we've got 4 blue and 3 red, okay? And I think, so we can see, as we expand how many are considered your nearest neighbors, the classification will change. Okay. Here is a test case at 1, 1. Okay, and over here, I think it's going to be red pretty much all the time, which makes sense, I think, visually. All right, so again, we measure the distance to every single other point, and then we're going to pick the kind of the nearest ones. So this is k is 1, it's going to be red. At k equals 3, we got red, we've got 2 red versus 1 blue. At k equals 5, we're still choosing red. It's still it's not like completely red. It's 3 red versus 2 blue. Okay, so there's still almost a tie, but it's not a tie. Okay, So 3 red versus 2 blue. So we would classify this as red. And at 7, we've got 4 red versus 3 blue. And so it's still going to be classified as red. Okay. So these are the 7 neighbors that are closest to here. And that's what happens there. Okay. Yes. How do you choose K? Yeah, basically cross-validation. So what we would do is we would designate some of these to be training and some of these to be validation, and we're gonna just see like how many errors am I misclassifying if I use K equals 1? How many errors am I making if I use K equals 3 versus 5 versus 7? And I didn't do this, but you can kind of create a plot to see like kind of your misclassification rate based on the different Ks that you've selected, okay? But yeah, you'd have to split it between training and validation. Okay, is that good? Here's a whole bunch of code to draw KNN boundary regions. This is actually basically the 2 important pieces are we're drawing a contour line based on we're creating a model. There's a package in R called class for classification, and the function that runs the KNN is called KNN. In your homework, I'm going to make you guys write up the KNN algorithm kind of yourself for like a simple case, okay? This, the KNN that is written in the package class R is a good KNN thing, and if you ever do KNN in real life, use this, okay? Don't use your hand-coded KNN, because this has a lot of nice features and is pretty good. And generally, KNN is not a probabilistic classifier, but KNN has the option to return probabilities of classes rather than just a hard assignment. And so the probabilities would be something like, oh, here's your 7 closest. Then the probability that this point is red is going to be 4 divided by 7 and 3 divided by 7 for blue, and things like that, okay? But generally in KNN, you go with a straight assignment, okay? But the reason why we want the probability thing is because we want to figure out the points where we're getting basically ties between red and blue here, okay? And this will allow us to figure out the boundary that this thing forms with red and blue, okay? So that's what all of this stuff is. It's just it's just like we're like trying to wrangle the output of KNN so that it creates this nice grid, and we can draw a contour line where at the contour where the probability is equal to 0.5. Okay, so this is the same points of data here. Somehow my picture got shifted down because it's outputting a message here. How do I suppress messages? Is it message equals false? Huh? Warnings equals false? This is not a warning though. It's just, let's try this. Okay, there we go. Message equals false, not messages. All right, so it's the same data here. It's supposed to be, I think, if we stare at the dots. Yeah, they look the same. Okay, and so now I've got this grid of so so we're bringing our computer to our knees, but it's basically like there's tiny, like in the PDF itself, there's tiny little dots, and it calculated the probability for every single one of these tiny little dots. It looks like it's shading and coloring, but they're actually just tiny little dots, and it calculated what's the kind of the KNN classification here, and it's gonna return, and it's coloring them red or blue, and then it's drawing a line to kind of connect all the spots where the dots are like 0.5, okay? And so this is what we get with when we're choosing the one nearest neighbor, okay? And so we can see that, if you look, this boundary here exists because this point is, like, if we pick a dot right here, it's equidistant to this point and this point. So if we're doing the one nearest neighbor, these are equidistant, and so that's why points on this side of the line are red and points on this side of the line are blue, okay? And then, and we're basically getting a line right between these 2 points because, if I pick a dot right here, it's like equidistant from the blue and equidistant from the red. So if we're doing I should have written with k equal to 1, you're going to kind of get this funny boundary, all right? And this might be just slightly, maybe not slightly, a lot overfitting our data here, okay? With k equals 3, it kind of smooths out the stuff, okay? And so things over on this side, even though there's a red dot here, if we pick this point right here, the 3 closest will be this blue, if we pick right here, the closest will be this location, this location, this location, and so it's gonna get classified as blue. Whereas if I move over here, then the 3 closest will be this red, this blue, and this red, and so then it will get classified as red, okay? And so this boundary here is saying, the 2 closest are red and blue, and the tiebreaker along this boundary is either going to be this point or this point, and that's where we're getting kind of these boundaries drawn. Yes, question?
Is the boundary always split it into 2 regions, or can it be like?
Yeah, you'll have enclaves, or exclaves, or I don't know what do you call it, like Lesotho inside South Africa? That's like stuff like that happens, okay? I think it's an enclave. I don't know the political terminology here. Yeah, so that happens depending on your choice of K, okay? And so, so the question is, do we want that? Maybe we do, maybe we don't. Generally, the existence of enclaves in your classification boundaries is an indication of overfitting of your data, because basically you're saying if anything looks almost exactly like this one particular case, it's going to be classified as this. But anything that's slightly different from it is going to get classified as something else, right? So, so I don't know. Okay, so that's k equals 3, and basically as I increase my k, it's going to kind of smooth out this boundary, and so KNN, also is subject to the bias variance trade-off. Lower k's will have less bias, more variance. Higher k's will generally be more bias, less variance. Okay, so as I do k equals 3, we can see the boundary misclassifies this red and this blue, but this seems to be doing a fairly okay job. At k equals 5, it kind of just smooths it out a little bit more, and we get 2 misclassified points of the red and no misclassified points of the blue. And with 7, I don't know if this is any smoother than what was earlier, but this is kind of the boundary region for 7. Okay, and I didn't go much higher, but here is like I just added more data. Okay, because over here we don't have a ton of points. So here I've made more data. Okay, and so so we'll do k equals 1. Okay, and with k equals 1, we see kind of these enclaves forming. Okay, and it really tries its best to, like, well, it actually doesn't care. It's not like trying its best. It's just following the rules of the algorithm, right? But the rules of the algorithm says, yeah, with this thing, if you're in this region, the closest dot to you is this blue thing, right? If you're along this line, it's going to be a tie between this blue dot and this red dot, and so anything on this side of the line is red, and anything on this side of the line is blue. And then you can see the border forms also right between these two things, and all of these points are equidistant here, okay? And so we're getting all sorts of stuff. This is k equals 1. And this certainly looks like it's overfitting, okay? Because it probably doesn't make sense that these should be classified as blue over here, okay? And likewise, this one shouldn't be. Although, you know, I'm surprised that we even get like this. I was expecting like way more enclaves and weird shapes here, but like you get something that's like kind of a little, that was more continuous than I expected. So this is what we have here. With k equals 3, we can start seeing things, you know, these boundaries forming here. K equals 3 actually gets a lot of the training cases wrong because of kind of these weird 2 blue dots out here. Like the point right here, the actually, no, what is it? I'm sorry. So like this point right here, the 3 nearest neighbors are actually this dot, this, and this. And so, so these all get classified as blue. And it's only until you get across this line that, I'm not sure which ones are the 3 closest neighbors. But this actually misclassifies our training data a little bit. With k equals 5, our borders get a little bit better. Yeah, you got weird things like this. Dots inside here, you know, these are these 2 blue dots and this red dot are the nearest. And so even though this red dot is right here, it gets classified as blue. So, but as I increase k equals to 5, things smooth out a little bit more. But again, you know, we're still getting a little bit of weird stuff right along the borders. Okay, and at k equals 7, we're trying to reduce kind of our weirdness. And then so I just kind of jumped up to k equals 20, and it's kind of just picking this line that says, all right, everything on this side is red and everything on this side is blue. Okay, and I think that's all I had for today here. Okay, so as far as, but you can kind of play around at least with, I think this code should work as far as drawing KNN boundaries here. Okay, have a good weekend, you guys. We'll see you next week.